that. I'm going to record a message right now.
Yes.
Is it starting recording?
Yeah. All right, I am. I'm officially recording now, so don't say anything stupid.
I wanted to miss your Lawson's class too.
All right, so let's talk about what we're doing today. So today I'm going to try and cover all of Resistor Circuits. On Monday I'll try and cover all of capacitor circuits. So get excited for that. So going through, the big idea here is that I can start using the stuff we learned in electrostatics to like make charges move, and then if I can like make charges move through a circuit, I can do cool things with those circuits. The most basic units that you'll see in circuits are resistors and capacitors, so that's why we're going to start there. If you go to college and major in anything that's going to require you to do like electrical engineering or anything like that, you'll learn so many more circuit elements and all that kind of stuff. This is just kind of like the point of this unit is just to get you like an introduction into how circuits work, right? So we're going to talk about resistors, we're going to talk about capacitors just to give you that intro. Does that make any sense? Mm-hmm. So starting here, on the agenda, we'll talk about currents and circuits in general. This is the first time we'll see this. And then we'll talk about resistivity, which is like a property that materials have. Then we'll turn our attention to like resistance of like individual elements. Then we'll talk a little bit about ohmic versus non-ohmic resistors, because that's an important distinction that AP wants you to have. We will also, after that, we'll do another presentation, which will talk about kind of the foundational, like how we get the foundational equations that we use to solve circuit problems. So I'll give you the parallel and the series circuits concepts. And then we'll close out by looking at combination circuits, or circuits that use both series and parallel elements. Does that make sense? So that's kind of what we'll be going through. And then we'll repeat that whole process with capacitors on Monday. Cool? Okay. All right. So getting into it, here's the idea with circuits as far as like we're concerned in this class. So a circuit for us is going to consist of some sort of voltage that's supplied. Remember, all voltages is potential, right? So we're just providing essentially an energy difference that will cause charges to move, right? That's what we're doing. So sometimes I have this picture in my head that I don't know how conceptually accurate it is, but it's kind of helpful of like you know, like if you have like a waterfall, like if I ran water across the waterfall, it would fall, right? And then I could put like a turbine or something down there to like get turned by that moving water flow. Does that make any sense? Mm-hmm. I tend to think of things like batteries as like pocket waterfalls, right? It provides the potential for things to move and do things, right? That's what it is. It's like energy that's available in that way. Does that make any sense? Mm-hmm. Now, you'll see, if you look on the internet, you're going to see all sorts of analogies similar to that are super problematic. So I try to typically avoid analogies because I think they end up causing more confusion than anything else. So just be aware, if you start looking at analogies online, people making videos about comparing circuits to flowing water or whatever, it tends to be problematic. I would try to avoid that. A bit of it will help you pass the AP test or like get through this little bit of the course, but it's going to give you all sorts of misconceptions because oftentimes we're going to talk about circuits as if they're powered by moving charges. It's actually that they're powered by the electric fields that are set up, and the moving charges are just happening concurrently. There's a really good video by Veritasium that talks about that. That's like when you light a light bulb on a circuit, you're actually not lighting it because charges are moving, you're lighting it because there's an electric field that's set up within the light bulb. Total side note, not why we're here, it would take all class to explain that. But be aware that as you like get into like looking into different videos and stuff, a lot of people that are well-intentioned create these analogies that are problematic. So if you're planning on like this being your only physics course and getting done and moving on, it's probably fine. If you're gonna like try to go major in any field that requires physics and a good understanding of electricity, I would try to avoid those kinds of videos and instead seek out resources that don't use analogies, but instead teach you directly what's actually happening. Does that make any sense? Mm-hmm. That's my parting wisdom on that. So what we do say though then is that we have something like a battery that provides this difference in energy levels, and that difference in energy levels is going to cause, you can think of it this way, it's going to cause like electrons or charge within the circuit to fall, right? It's going to charge it, it's going to cause it to travel along that pathway. It does that by setting up an electric field within the wires that then the charges will respond to and they'll move. Now, that moving charge is what we call current, okay? So current is how we communicate that charges are moving. The more current, the faster the charges are moving through, the less current, the slower the charges are moving through. From this point forward, we will reject a lot of the conversation we had about what's actually happening with electrons moving and whatnot in favor of what we call conventional current. So you got to understand that like a lot of this was all worked out a long time before we really understood what was happening microscopically very well. And in that time period, we developed this idea that positive charges are what does all the moving. And so everything we look at from here forward is basically going to be talking about things in terms of what we call conventional current, which makes the assumption that positive charges are what are moving. And so we'll imagine that current is moving from the positive to the negative terminals of batteries, even though what's actually happening is the opposite. That's what we'll imagine is happening. Does that make sense? And that's okay, it still works, right? Like we saw this with charge earlier too, right? It's kind of just an accounting trick. Like if negative charges are doing all the moving, it's kind of like positive charges are moving the opposite way effectively, so it's fine, it's not a big deal. And all of circuits uses this basic mentality, so it's okay. All right, so when we talk about current, it's the rate of charge flow. We measure charge in coulombs, and so we measure current in coulombs per second. No one wants to say coulombs per second all the time, so we shorten that to the ampere. And ampere is not something people like to say either, so we typically just shorten that down to amps. So when you hear the term amps or read the term amps, that is talking about current. One of the biggest differences in different like battery technologies is not the voltage of the batteries, it is the amperage of the batteries. So if you've ever wondered like why are AAA batteries and AA batteries and D batteries, like why are they different? It's actually not the voltage, they're all 1.5 volts. What makes it different is that they have the chemical capacity to supply a higher amperage. Does that make any sense? That's the difference. It's not that they're different voltages. Does that make sense? This is true too when you go to like buy batteries for your car. All car batteries are 12-volt batteries, but you'll see them be rated in different CCAs, which are cold crank amps. That tells you how many amps the battery can provide when it's cold. So just side note there on what you see out in the world. So we define 1 amp as 1 coulomb per second. That's really all you need to know there. Cool? Mm-hmm. Yeah.
What about like coulombs being too big and you have to make it to like microcoulombs?
That doesn't pop up so much in circuits. It turns out that an amp is quite a bit of current. So you may see things, depending on the type of circuit, you may see things in like milliamps instead of amps. A lot of your household circuits will still communicate things in terms of amps because houses use a lot of current. What you'll see is that like handheld devices tend to have currents measured in milliamps though. So it depends on the context of what you're seeing. Like a standard household circuit is going to be about 12 amps rated, which means it's rated to allow 12 amps to be flowing at any given moment before it breaks the circuit and all that. But your phone, almost all the communication that's going on there is in very small amounts of current, like milliamps. So it just depends on what you're working on. You could see either one. That make sense? Mm-hmm. Good question. All right, so there's this property that matter has called resistivity. Okay, so you're going to hear me talk about resistance and resistivity. Resistivity is the property of matter that resists current flowing through it. And if you think about it on the like microscopic level, we have some sort of substance that has a structure, and that means that there are, you know, nuclei scattered throughout the material, and I'm trying to basically, if I'm putting a current through it, I'm trying to pull electrons through that material, but those protons are going to have some sort of attraction to hold on to those electrons, right? And so that means they're going to resist those electrons being pulled away, and that leads to this property called resistivity. So that is like literally what's happening, but sometimes people will use the analogy of like trying to pass water through a filter, where it's like there's some sort of physical barrier that slows down the progress. Not a bad analogy to think of, but that's kind of what resistivity is. It's slowing down the flow. When we talk about conductors, we tend to think of them as ideal, so there's no resistivity, but in reality, most conductors have resistivities that are just very, very small, and that makes them useful. We use this rho for resistivity. So you probably remember that we used rho for density. It's popping up here again, but they're totally different contexts. So you won't ever see them used in the same question or anything like that. There's no reason to be concerned about those. Are we okay with the basic thing of resistivity? Mm-hmm. Now, if I'm trying to design a circuit, I can take some material with a certain resistivity, and I can take that material and I can put it within a certain shape and put it in a circuit to make a resistor. So a resistor is something that's designed to give resistance to a circuit. Okay? In other words, it's meant to slow down the flow through the circuit. So a resistor, I can make one by having a material with a certain resistivity and just changing the physical shape of the resistor. So I can change its cross-sectional area and I can change its length. So I want you to notice in this equation that the length is on top, so that means the longer a resistor is, the more resistance it will offer. But the area is on the bottom, so that means the wider the resistor is, the less resistance it will offer. Okay? Normally I have you guys tinker with a program to like mess with this stuff, but we don't have time for that today. Make any sense? Mm-hmm. I thought you were taking notes, and I was about to interrupt you.
No.
Alright, so are we okay with this idea of resistance and resistivity? They're different, but they contribute to one another. Alright, so this brings us to the idea of ohmic resistors. So we should always have this conversation about ideal things versus real things. Okay? So most of the time, we will treat resistors as what we call ohmic. That's the ideal. What that means is that with an ohmic resistor, there's a linear relationship between the voltage I put across the resistor and the current that goes through the resistor. In other words, if I double the voltage, I double the current. If I quadruple the voltage, I quadruple the current. However, most materials only have a small band of voltages within which they behave in an ohmic fashion. What really happens is you kind of see these critical points where there's not enough voltage to get anything to move, and then on the higher end there's a voltage that's high enough that it actually starts to break down the material and current accelerates through it at a much higher rate. So, you need to be familiar with this idea that things kind of have a band in which they behave ohmically and a band in which they behave non-ohmically, and then you can, through experimental means, determine that band or determine if something behaves ohmic at all in general, right? So that's easy to do. I just take a resistor and I put a bunch of different voltages across it and I measure the current through it, and then I can kind of figure out, at what point that deviates from behaving as an ohmic resistor. Does that make any sense?
Yes.
Okay. And we get out of this Ohm's law, which is super critical for all the circuit stuff we're going to do with resistors. So Ohm's law is that the voltage across a resistor is equal to the current through the resistor multiplied by its resistance. Does that make sense? That's the way that it's normally written. It's not the most helpful for when we talk about what it means to be ohmic. So I prefer to write it this way. This is a more helpful way to think about Ohm's law than what it's telling me is that as I change the voltage, there's a linear relationship with the current through it. That's really what Ohm's law is there to tell you. However, it's extremely useful mathematically, and that's a more convenient way to write it for math. Does that make any sense?
Mm-hmm.
Okay, that's it for the idea of resistance and current and all of those kinds of things. Do you guys have any questions about what we're doing with the basics of a circuit, what's going on with resistance, any of that, because we're about to start applying it?
No.
No? Okay. Alright, so the next bit then is we should talk about how we deal with lots of resistors in a circuit. So what we're going to talk about are two different ways that a circuit could look. I'm going to start by talking about those two different ways, and then we'll get into it. So the first way that a circuit could look is like this, where I've got a battery. So this is the symbol for a battery in a circuit. And then I have resistor elements within a circuit. We define a series circuit as a circuit in which all of the elements are in a nice linear order, right? If you watched closely while I drew this, I never had to pick up my pen because I hit them all in a series, right? 1, 2, 3, all the way through. Does that make sense?
Mm-hmm.
A parallel circuit, on the other hand, is one that's going to look like this, where it exists in branches. So I want you to see that in this one, there's only one pathway that all the current through the circuit has to follow. In this circuit, I reach branches where my current can break, and some could go this way and some could go that way. Some could go this way, some could go that way, right? That is how we define a parallel circuit, is when there is branching for the current to follow. Does that make sense?
Mm-hmm.
Okay. These different circuits behave differently, okay? The reason for that is that if I look at this circuit, I can see that the current is one pathway all the way through. And what that means for this circuit is that the current is constant. Every element in the circuit is going to have the same amount of current going through it. Does that make sense? However, what's going to happen is, as I go around the circuit, I'm going to see what we call voltage drops. So what that means is that I'm going to have a little bit of a voltage drop here, a little bit of a voltage drop here, and a little bit of a voltage drop here. And those voltage drops across the entire circuit, or around the circuit, they're all going to add together to the source. Okay? So if this is a 5-volt battery, that means that as I go around the circuit, I may drop 2 volts here, I may drop 1 volt here, and I may drop 2 volts here, but as I go around, these are all going to add up to the source. Does that make any sense? Okay. What we see with parallel circuits is essentially the opposite. Because all of these batteries have a direct pathway, all of the resistors have a direct pathway to the battery, that means that they actually all have the same voltage across them. So in this one, what we see is that the voltage is constant. Maybe constant's not the right word, but it's all the same. And instead, that means that the current is branching off. So what I should see is that the current through this branch, plus the current through that branch, plus the current through that branch is going to add up to the total current of the circuit. And that's just conservation of charge, right? Whatever charge I have coming this way, it better be coming back the other way. Does that make any sense? So this is how we look at this one. So the current adds and the voltage is constant. For series circuit, the voltage adds and the current is constant. Does that make any sense? So different types of behaviors depending on how I arrange them. And that leads to different things. Cool, cool? Now what we're going to be most concerned with for today is it would be convenient to be able to determine what the equivalent resistance of each of those circuits is, right? Like, let's say that I had, let's say that I hid this circuit behind this thing here, right? And you don't know what's there. It would be nice to know what current I would expect to be flowing through that battery. And the only way that I'm going to know that is if I can figure out what the equivalent resistance of that circuit is. Does that make any sense? Mm-hmm. Same thing over here, right? I want to be able to know like what's going to happen to my battery if I put it in there. So what we need to figure out then is how can I determine the equivalent resistance within those circuits? And there's fairly simple equations for it. And one of my objectives here is I want to derive those equations for you so you can see where they come from. Alright, so a lot of these first couple slides are going to talk about what I already said. So in a series circuit, all elements flow from one to the other, and that means that current is constant throughout the circuit, but the voltage will vary, with the added bit that the voltage should add together as we go. Are we cool with that? Mm-hmm. Okay. I didn't want you to see that yet. I was going to do the math for you. So let's make that assumption, and I'm going to try to quickly work out what that means algebraically. So let's say I have a circuit like that, and I want to try and figure out what the equivalent resistance is. Well, I'm going to work this out not as if I had 3 resistors, but as if I had infinitely many resistors, because then we'll have a universal statement, right? So what I'm going to do is I'm going to say that the most important mathematical tool in this couple of statements here is that the voltage is all going to add together, right? So here's what I'm going to say is that the voltage through the battery is going to be equal to the voltage across each resistor. So I'm going to say the voltage across the first resistor plus the voltage across the second resistor plus on and on and on until I get to the voltage across the nth resistor in series. We okay with that? Yes. Now here's what I'm going to do is I'm going to use Ohm's law for each of these. And so what I'll see then is that for the battery, that's going to be the current multiplied by the equivalent resistance of the entire circuit. For each of these resistors, it's going to be the current multiplied by the resistance of that circuit, or that element. And the other important statement I have there is that the current's the same throughout the entire circuit. So I know all of these I's are the same. Are we okay with that?
Yes.
Okay. If they're all the same, then I could divide them off, and they're all going to cancel out, leaving me with this statement that the equivalent resistance is just equal to the simple sum of all the resistors. And that's how I get this. This, I believe, is the way that it's written on your formula sheet. So the equivalent resistance for a series circuit is equal to the sum of all of the elements. If you're not super familiar with that, like summation notation, I don't really have the time to help you out there, but that's how it's on the thing. Are we okay with that? Okay, so that's how I get that equation. This is a very useful equation, and now I have it. So let's look at parallel circuits. So for parallel circuits, we have the opposite case, and so what you're going to see me do is basically like the opposite algebra. So I'm going to start with this idea that the current through the battery is going to be equal to the current through each branch. So I'm going to say the total current is going to be equal to the current through branch 1 plus the current through branch 2 plus the current through branch n. Just like before, I could use Ohm's law, so V equals IR. I could use it in this form to say that I must be equal to V over R, so that this total current is going to be equal to the voltage of the battery divided by the resistance equivalent of the whole circuit. Cool?
Mm-hmm.
And that's equal to, I'm going to have the same substitution for all of these. The current here, well, because they're all hooked up directly to the battery, that's the same voltage, right? That was one of the things we talked about. So they all get the same voltage. So I'm actually going to take this subscript off, and I'm going to say that this is the voltage for the whole circuit divided by resistor 1, plus the voltage divided by resistor 2, plus on and on, the voltage divided by resistor n. Now it shouldn't be too much of a stretch here to see that I've got this same common voltage in all my terms, and so guess what? I can divide that off. I know y'all don't really like fractions, but you should be okay with the idea that I can divide that and it'll cancel these out just fine, and then I end up with this statement that 1 over the equivalent resistance is equal to 1 over the resistance of the first, plus 1 over the resistance of the second, plus 1 over the resistance of the n. Now, before I show you those equations, here's what I want you to see here. With series circuits, the relationships are fairly intuitive. They make sense because it's all nice and additive, no big deal. This whole reciprocal thing that's happening in this equation makes parallel circuits very non-intuitive. So when you're solving especially conceptual questions, don't rely on your intuition because your intuition is going to be inaccurate. Rely on the math. You have this statement here, use it. Does that make sense? Okay. So here's what we get here. Notice the other writing that they use. This is equivalent to that. 1 over the resistance of parallel is equal to the summation statement here. I'm just adding all the elements 1 over the resistance. And so that matches what I have there. Does that make any sense?
Yeah.
So the real sticky part of solving circuits comes down to figuring out what information you have and then how you get the rest. My advice is to always, if you can, determine what you know about the circuit as a whole first. So determine the voltage of the entire circuit first, and figure out the current of the entire circuit first, figure out the resistance of the entire circuit first, because then it's easier to take that big idea and talk about all the individual elements. I don't have time to work through a whole bunch of circuits questions for you. Y'all are just going to have to figure that out next year. But that's my general advice, is to start with looking at what I can determine about the circuit as a whole, and then work backwards from there. All right, that's it that I have here for these resistors in parallel. Do you guys have questions about that? Okay. So that's going to bring us to having to deal with these things put together, which is this worksheet here. So if I have a circuit like this, let's say that I have the job of determining the equivalent resistance of the circuit, and then also finding the current through all of these elements. This is kind of your one shot at an example you're going to get from me here. I'm going to walk you through how we could do this process. The first thing that we have to do is determine the structure of the circuit. Now, every circuit is going to behave overall either as a series circuit with parallel elements, or it's going to be overall a parallel circuit with series elements. Does that make any sense? Here's what I mean. If I look at this circuit, what I want you to see is if I start tracking the current through it, I'm going to see that it goes along and I hit an element first, right? Before it splits. So this is going to behave as a series circuit with parallel elements. And then if I keep tracing it, now I can see where I'm splitting. I can see that it's going to come back together on the other end. And then I've got another element in series. So when I look at this circuit, if you just trace the current, what I'd like you to see is, what I really have here is I have this resistor 1 in series with this parallel component, which I'm gonna call RP, which is in series